Okay, we have Will Scott on the stage now, who is going to talk about messaging without metadata.
Cool. Yeah. So the basic structure of this is to sort of survey over what is going on in secure messaging. So the different efforts that are working on sort of different problems, and to try to systematize a little bit the different threat models that we're trying to address and what's left and what's happening there. Right. So in the context of messaging, we've got people who want to talk, and we've got some network in between that is managing getting messages back and forth, and we've sort of split this into two things. Maybe there's asynchronous email style, where the server is responsible for holding on to things for a while, and then there's the instant messaging, the chat, where we're just sort of relaying it, but we still have generally some infrastructure that's doing that. But this ends up being sort of two different solution spaces. There's two different types of systems that are getting built, one on trying to secure emails and how do we do that better, and a different set on how do we do better on our instant messaging side. The thing that we've really, I think, as a community had success with is end-to-end encryption. We've got Signal, and that's really taken over the instant messaging side. And then email has, we have solutions. There is GPG and a whole set of encryption things that aren't nearly as prevalent. And there is a large set of efforts right now, I think, to try and figure out how do we get the same ubiquity of end-to-end encryption on an email style transport that we have on instant messaging. And so what we got with Signal was this axolotl protocol, where we are, with each message, providing a new key for the other person to use as they respond, and we're ratcheting through the encryption key that we're using, which gives us a couple sort of properties that are useful for this format. And those are forward secrecy and deniability in a semi-asynchronous setup. And so I think that's where I want to start, is talking about what these properties are, and then we'll keep building from there. So in terms of this forward secrecy and deniability, what this is talking about is what happens if one of these devices gets compromised. Either key material gets leaked, or the device actually gets captured. What Signal gives us with this ratcheting of changing keys is that with one participant, even if they've kept all of their network logs, afterwards they can't prove that it wasn't them who said what the other person messaged to them. That by releasing and changing keys each time, the Signal protocol has this nice property where I, as one of those two participants, am able to have reconstructed that whole thing purely from my side. I now know enough in what is released in the new key that comes in these new ephemeral keys. Part of that message is to release the additional key material from the previous one, so that the whole conversation up to the last message is something that a single participant could have all done themselves consistently. So that if they turn this over to the authority, there's a potential that they just made it purely themselves. And that's sort of a cool property technically, that we can say, this is cool. Unlike, DKIM on emails, I can't prove it was actually sent by this person's servers. That someone who sees the leak, says, well, maybe you just did this yourself, and there's no way to deny that. And then we also have this sort of asynchronous thing where the key exchange, the initial handshake that we're making to set this up, one of the participants can be offline and do it a little bit later, and the protocol still works. So that's the other major sort of crypto thing that we got recently on these instant messaging things, is a lot of times, like with the initial OTR handshake and things like this, both participants need to sort of relatively quickly complete this handshake, and you've got some periods where you're sort of in a dangerous partially created state, and now we've got something where we can sort of wait partway through and finish this. And so what this has given us is that Alice and Bob, our two participants, can talk to each other, and the server is passing messages back and forth, but it doesn't know the contents of those messages, right? So end-to-end means we've encrypted the contents, but there's still a lot of things that the server knows, and there's still a lot of things that the network knows, and this is the metadata. So we've got this threat model that we are starting at. This is, I think, in a lot of ways for us as a community, the baseline, where at least we want to be able to ensure that the network and server that's sort of passively watching, we want to be ready for them. If someone is trying to surveil the contents of the messages, we want to make that hard for them. So we've got these base set of things that we're able to say, okay, even if this is happening, which it probably is, I'm good, right? I've got this end-to-end encryption thing. These are things that they can't do. But there's a lot of stuff that this doesn't cover, right? And so I'll get there in a second. I guess let me finish on the Signal side first. Signal's now in a bunch of apps. So we've got this sort of ubiquity of Signal now. And the, I think, development of sort of the Signal protocol, where that effort has gone is into a bunch of how do we now expand this to multiple parties? So how do we go from the one-on-one to a group chat setting? N+1 sec just came out, but we've had a couple earlier. So ASN did, I guess it was Piccolo and now is Flute, which is over IRC. How can a group do an encrypted style messaging? And then we had Mega's MP Inc. Earlier as sort of like the proof of this. We actually do know some of the crypto and algorithms for getting the multi-party thing working. So what's left? The server knows a lot. It knows when each of the users is online. It often knows the user's contact lists, right? So with Signal, the server knows who your contacts are. It knows when you are sending messages and to whom. And it knows the size, so it knows how big these messages are. And that's a lot of metadata. Right, and this is the classic trope that this is enough for the people who are surveilling us, that we haven't really fully solved this problem or closed the window of hiding our messages. So what are the new ideas? How do we get past that? So we've got our baseline of we've encrypted our contents. How do we make this metadata a little bit less easy to get? I think a lot of new ideas came out in Pond. So this was a while ago, right? So Pond was saying, how do we do better for a network adversary? How do we do better against what this sort of NSA style monitoring has? And it did this by having a network protocol that tries to protect against a bunch of things. It's going to send fixed-sized messages, and it's going to send them sort of irregularly, regardless of how much you're actually sending. So as an envelope around your actual transmissions, it will, every few minutes, send a message to the server and get a message back from the server, regardless of whether you actually have a message to send or not. So it's going to try and keep the communication pattern constant. Pond, as a result, is flipping more to the email side. It's sending that message every few minutes, and so you're not going to have the real-time communication as easily. It also comes up with this, one of the early implementations of a protocol called Panda for adding a new contact, where the goal is how do I add that new contact without having my whole contact list in the server. So I need to exchange these initial keys. I need to send them to someone. Often we just sort of say that's out of scope. That's not, right? This is our out-of-band initial rendezvous to have a secure channel. Well, what is that? And so Panda is saying, well, actually, we probably don't necessarily have that, so how do we bootstrap this initial thing without the server knowing who those two people are by some unique handle or identity? In terms of communication, it's doing this thing called an exponential decay, which is a cool idea in terms of how often you're sending messages. So you have this curve that has the property that at any point in the curve, the probability distribution is sort of the same. So in terms of rare event statistical probability, just because I've waited 5 minutes, I don't know if the next one will come any sooner than if I hadn't waited those 5 minutes. And so it's hard for the server to predict if a client has actually gone offline or has just hit the long tail of this probability curve, right? So it's the server can probabilistically say, well, it's been 2 hours. It's less likely that you're still online, but it doesn't know for sure for a while. So you get this grace period of jitter and being able to sort of make someone who's watching you less sure about what you're actually doing. So we've got this property where I'm just sort of sending messages regardless of whether I actually have something to say. And so this sort of updates our threat model. Is this going to keep doing this? No. Where now, if we have someone who's trying to watch the traffic patterns, we're also protecting against them. So we've got one additional thing. But the server still knows some things, right? So the server knows when there's an actual message versus not. So we're not hiding the frequency of messages and when I'm actually sending and receiving messages from the server, because the server does have the concept of some identity that I'm sending this message to, and I don't now have the same linkage of all of my contacts to my user as much, but I do have this property that the server still knows when I'm actually active in sending messages versus when my client is online. Okay. Cool. So the point was, so the server doesn't actually know when you're sending, but it knows when you're getting messages that you're receiving. So the identity is sort of the mailbox destination, and that's what the server is able to see, but it doesn't know who's sending. I guess the other thing on protecting the network is the PON traffic goes over Tor. So your IP address to the server is anonymized over that Tor relay, which is giving you, right, we're in an asynchronous model. We certainly don't care about the latency, which is pretty minimal that Tor is implying, and that gives us an additional sort of delinking that my connections are going to come from different places. The other asynchronous thing that we've got that came out somewhat recently is called Loopix. This is on the mixed network side. And so this is, I think, sort of a modern reimagining of some of the early mixed style networks. So we got this is a concept that came out fairly early in email. I think if you have Mutt as an email client, you might see that there's this mixing option deep in some of the sending options that you can use to do a mixmaster style routing of your emails. And there's now sort of an attempt to bring that back. Loopix is basically the thought here is I'm going to send my messages not through a single server, but we're going to have a chain of servers. And each of those servers internally is going to shuffle a set of messages. So it's going to wait, collect a set of messages, shuffle them in a way that it knows, pass them on to the next one that will also shuffle them, and pass that set on to a third one, and however long your chain goes. And each of the servers will shuffle them. And so by the end server, it won't know which message is coming from which client. And so in a similar style to these multiple hops to delink that we see in a Tor system, what a mixed system is doing here is, unless all of the nodes on your path are sort of colluding and talking to each other, at the end you've got this set of messages where you don't know which message is coming from which source. And by doing it in a batch, you're ensuring that you're getting this K anonymity, where some set of messages K all got batched initially, but they were encrypted. So the initial guy who was waiting for that batch to form just knows, okay, so I got messages from some set of people, but they're all encrypted and they're all fixed size, so I don't know much about them. I'm going to shuffle them around. I'm going to give them the next person who shuffles them around, and the next person who's, shuffles them around and has decrypted enough now to see, okay, so I've got these messages with contents, but now unless I talk to all of these servers, I don't know, right? So by doing this batch, we're able to get this additional sort of level of anonymity where we now are trusting less about the servers to be able to say anything about who's active when. So this is an ongoing thing that a set of people are doing. David Staten and Yawning and a set of people are working on this under the name Katzenpost. And so we're sort of saying, instead of having this sort of fully distributed thing, if I have a few different entities that I trust a little bit, or at least not to collude, I can stop trusting the single server to know quite as much. This is, I guess, maybe also somewhat similar to Ricochet in a sense, right? Which is saying we're going to do messaging over Tor, and again, in order to not trust the single centralized server, we're going to use the Tor network itself as a set of relays, and we're going to send our messages through a bunch of different hops to do that. Right, if I've got a bunch of different hops, I'm not trusting any individual server with knowing sort of these paths and when I'm active. By splitting that out among a set of mutually distrusting servers, I can get similar properties. Ricochet also is getting some work under the Ricochet Go project or repo that is under that organization. So the current work is splitting the front end user interface, which is how we interact with it, from the actual protocol implementation, which is getting rewritten in Go, and that has both some security properties that are nice, that actual implementation of logic can get sandboxed a little bit better, and also maybe gives us some ability to have more flexibility in terms of the user agent that we're using. So you can now imagine potentially you've got a mobile client or something that talks to this Go implementation of the protocol, where you've got some communication between your different devices, and then you've got your agent that is how you're interacting with people. So again, we're seeing this set of mix approaches or Tor-based approaches that are trying to solve the server now. So in addition to our network adversary, we really want to prevent the server from being able to watch information about us, and understand the patterns of traffic. So either the timing, when I'm online, and who my contacts are. Right? We're trying to take. We're trying to add to our adversary model and add these additional entities that we're not sure we really want to trust. Cool. And then I want to talk about the other one as well, which is private information retrieval. And this is a thing that came out of Ian Goldberg's group a while ago, and has been getting, I think, mostly academic attention still, which is saying, how do we get a single centralized server and still know less about it? And so the hypothetical question to start getting this one, which I think is maybe, I'm going to spend a little bit more time and dive into this one, is how do I retrieve a message from a server without the server knowing which message I gave it, right? And so there's this sort of straw man answer where you say, well, if the server just gives me the whole database, then I can grab out the one that I care about, and I haven't told the server anything about which one I wanted. And so then the next question is, can I do that with a reasonable network cost where I haven't had to download the entire database? And PIR is saying, well, maybe. And so the basic idea is we're going to do something similar to this mixnet thing of distributing load. I'm going to have a couple or a few servers that I say aren't going to collude. And what I'm going to ask from the different servers is I'm going to say, hey, you XOR some set of your elements that I tell you, and give me that sort of superposition of them. And on the other one, I'll also ask for an XOR. And to each individual server, the request I'm making should look random. But if I then XOR all of the individual requests together, they should all cancel out. Because if I XOR something with itself, I get back 0. So if I ask for elements an even number of times, they cancel out when I XOR them back on my local machine. And so I've asked for a network bandwidth of 1 element from each of the servers, and then what I get back at the end is only 1 element that I've asked for an odd number of times. So I have this nice property from the client that I haven't revealed to the server which thing that it has that I actually have asked for, but at the cost that the server has had to take this request for a random subset of things that it has and do this math or this computational thing, which is, it's a basic operation that CPUs are pretty fast at. But still, if you have many users and many elements in your database, this is a lot of computation that you've sort of asked the server to do on your behalf. It has to read half of its database and put it all together. And so if my database is gigs and gigs, this is problematic, right? So this problem of scaling is really, I think, the thing that has caused people to say this is impractical. And that's a pretty good reaction. So with this primitive, what do we do? The thing that came out a couple of years ago is DP5, a privacy-preserving protocol. And so this is sort of like the presence messages in XMPP. If you're familiar with your Jabber client, there's sort of a couple basic types of messages. There's the actual chat message that you send, which is the contents of a message. And then there's the signaling of online and offline. And so what DP5 did was it said, okay, so we can't necessarily fit our whole protocol of chat through this mechanism because it's going to be very slow and it'll cost us a lot. So instead what we're going to do is we're just going to use it for initiating a new session. So when I have a contact and I want to begin talking to them, I'm going to use the PIR style message just once, to tell them where I am, and then we'll talk based on where I am currently. And so in fact, what I'll do is every conversation when I start it, I'm going to make a new Tor connection to an XMPP server. I'm going to register a new account, and then I'm going to use this XMPP or this PIR system, which is my long-lived way to talk to my contacts, and say, hey, contact, I'm now connected via Tor at this account. You should also connect over Tor to this account, and we'll chat on two totally ephemeral accounts that we only use for that single conversation. So I'm going to delink all of my conversations as totally separate sessions, and I'll use this long-lived, but with this theoretical lack of connection to get better anonymity where the server doesn't necessarily know how to link them. So I've split, again, I've got some data channel that's separate from my sort of long-term identity channel, and we can get it for that. At the beginning of, I think this year, they built the XMPP implementation of this and released it. So there is a thing called DP5 proxy that is the sort of, you run it and it acts like a local Jabber server. So you connect your XMPP client to this thing that's running on your local machine, and it does this translation where you have a normal looking buddy list, and when you initiate the connection, it does this PIR thing to the PIR server set that they're running, and then makes the new account. And so why are we doing this? Well, hopefully we're now moving up to a global passive adversary. So we're saying if someone, even if they can monitor a significant fraction of network traffic, right? So that's what we didn't necessarily get from Tor. Is Tor is great if we're talking about someone who has some ASs that they can monitor, or some set of these nodes. But if there's someone who can actually monitor a sizable amount of the internet or all of the internet and sees all of the different links, we need something where we're getting something more theoretical rather than just statistical to solve this, right? So that expectation that someone's not watching the whole network breaks down, and we need to go to this next step. Cool. So then I guess the final thing, and this is what I've been working on to try and extend DP5, is something that we're calling TALIC. And you can look at it and read about it if you want. But we're basically taking the same approach, and we're saying, can we actually scale it so that instead of having to do these two things as split, can we do it all just through this PIR mechanism? And so the question is, can we get enough efficiency out of this thing that it's practical for basic messaging? And so it's the same basic PIR thing, but the things that we're doing on it are two things. One is, how do we deal with writes? We're going to do something like Pond, where all of the clients are regularly writing some message to the server. It won't know which ones are actually a message to someone else or just a random message, as long as they're all acting the same whether or not they have a message to send. So you're doing the same thing there, and you're putting it somewhere random in the database. The way that you're coordinating with the person you're trying to talk to is the two of you are sharing a deterministic seed for your shared random number generator. So you both stay in sync and know which next random element in the whole database it is you're looking for. And because there's enough flexibility in this PIR request that the client can keep asking for and basically polling for the item where it expects that next element to be, that it can keep sort of doing that regularly until it sees the next message in the stream that's following this random number generator, and then update its random number seed to the next one in the series. So, right, if I've got the same seed, my random number generator will stay in step. The two of us will get the same thing. You don't want your database to be too big. There's a thing called a cuckoo hash table, which is basically just, we've got hash tables, right? So I'm going to take an element, I'm going to hash it, it goes somewhere in a known set of things. And the problem that we have with hash tables is, how do we deal with eviction? How do we deal with two messages ending up in the same place? This is where we have to deal with our sparsity. How dense can I pack this thing? And the thought here is, if each element actually has two different potential locations, so I have two separate hash functions, and so each element can hash to one of two places. So every time I read, I need to read in both of those places to see if it's in either of them. But that gives me a lot of flexibility, because whenever I go to evict, because I've now written too many things into a box, I can look at the ones that I'm going to throw out and say, well, you have someplace else, and maybe that one has a free spot. And so you have enough flexibility that you can load your hash table up to a density of about 95% full without having performance impact, which is pretty reasonable. So you can get a pretty dense database where you've compressed how big that final thing is. And then I think the thing that is maybe at the core of why this is interesting and why this is maybe not quite as crazy as we think, is that we've actually, not us as a community, but like this weird computer science AI community has spent a lot of time solving this exact problem, which is when I do the query on Google, or when I have to do my machine learning model lookup, it has to go out and look at a huge amount of data in parallel and then pull back some element. And really this PIR operation in a lot of ways is doing something very similar, right? It's going out to a lot of data, and it's doing a pretty simple thing to reduce it back down to a single item. And that looks a lot like what our modern GPUs are designed to do. They've got a lot of parallel cores that are able to do something simple, like an XOR operation, and pull back to a small amount of bandwidth that they can use to communicate between the CPU processor, that's the general purpose thing, and this GPU thing. So we've got the basic implementation of the GPU version of this, where as long as per GPU we've only got 8 or 12 gigs worth of data, we can do a millisecond or a few millisecond lookups for this PIR operation. And so we can get individual computers that can support thousands of requests per second, maybe even tens of thousands, but somewhere in that 1,000 to 10,000 range. And so that maybe gives us enough to do something that's synchronous, or if not synchronous, but what we expect from our messengers, right? Because I really want to be able to read every second I see the new message. Like if you write a message to me, I'd like to see it within a couple seconds if I'm gonna have a low latency conversation with you. Once it gets to order of 5-10 seconds, it starts to be a little bit harder to have that interactive conversation. But you could imagine a latency of 5 seconds that's enough to make this cost efficient. It's written in Go. There's a library that integrates, and it's this concept of a stream, basically, where I have a sort of a handle that I give to someone else, and then they can watch it, and I'm putting stuff into it. I set up a website that has the basics of how you can run this thing. There's a command line implementation of it that is pretty stable. I've put messages into it, and other people have been able to read them. So that's a start. But this is, we're sort of at the scaling from like me and a few friends to maybe tens or hundreds of people to make sure that this is actually working the way we're expecting. And then in terms of ease of use, so that it's not just a command line client, I'm most of the way done, and it's linked here on this page for the same sort of XMPP style shim, where you can use an existing Jabber client, and you'll just talk purely to this backend system rather than the DP5 style thing, but to get some UI on this that's easier than just a command line client. I think more generally, the thought is we've got these trade-offs, right? Signal everyone is using, but I'm trusting the server quite a bit more. Mixed networks are giving me a good style of anonymity, and what I'm trading off for that is latency, that in order to ensure that I'm getting that guarantee of anonymity, I'm potentially waiting a while. Tor is mostly about this global passive adversary of, am I willing to believe that the set of nodes that I'm hopping through are disjoint enough that no one's able to watch and correlate my traffic across, my entry and exit. Right? If I'm talking to someone that I know is also on Comcast, right? Like if we're both on the same ISP and we're both in the same country, well, it sure sounds like there's some adversary who potentially can see those two ends, and is the traffic pattern shielded enough to prevent them from linking those two communications. And then we've got this PIR primitive, which is computationally quite expensive comparatively, but does give me the same sort of mixed style. I only have to assume that one of the end servers that I'm talking with is trustworthy. that unless all of the different servers that I've chosen are colluding together, I get some theoretical guarantee, which is what we might hope for. So I think this is, as I understand it, where we are, and the things to be thinking about is, are there other like primitives that we can have that give us other ways to get these properties to reduce metadata, or how do we develop these sets of primitives that we already have to get somewhere where an adversary knows a lot less about us, because we've got a long ways to go from anything that's getting real use right now, to prevent people from knowing when we're talking and who we're talking to. Cool.
Yeah, very cool. Does anybody have questions? Yes.
So your Go implementation is only the front end, or?
All of it.
So your Go implementation, the 2,000 lines or 5,000 lines, is only the front end, and you still rely on the DP5 for the server side?
No, that implementation is all of the components. So it's three pieces. There's libtalic is a client that will talk. It'll do the encryption operations for a PIR style reads and writes. There's something called the front end. The way we have it set up is the client will only talk to a single front end, but it will encrypt its message to the different servers, and the front end will then talk to what we're calling replicas, which are the different trust domains, the different entities that are actually running that. So that's again to like minimize the network bandwidth between the client, if it's mobile, for instance, and who it needs to talk to. So it basically sends a request to each of the different trust domains, and then there's this front end component that basically batches up a set of incoming requests over a time period and sends the batches to the appropriate replicas. And then there's the replica code, which actually does the PIRs on a batch. The replica code, there's a pure Go CPU-based implementation, and then we have both a OpenCL and a CUDA GPU thing that it can talk to using Go bindings to those two.
Are there many of these replicas running yet, or what's the current status of
these things? So I put up and on this link there's a sample like conf file that you can download that is the working alpha instance that I've been maintaining with a friend. It has two nodes right now, one that I run at the University of Michigan and one that he runs at the University of Washington. So you're trusting us basically not to collude, which is probably a bad assumption. So right now that's like a pretty simple like proof that this is working and operating correctly per protocol. What we really want to do is get a set of probably 3 that are GPU based and can do the sort of higher scale of messages.
So for 2 people to communicate with this, do they need to be using the exact same set of servers, or would it be okay if I was also sending messages to a server that you're not? I mean, it seems like we just need an overlapping set of servers, and we're obviously relying on the intersection of our 2 sets. But
so what you need is when I make the request that is this XOR superposition of the different server databases, those databases need to be in sync so that they cancel out. So if I ask for item in position 1 from server A and from server B, they need to cancel out to 0 appropriately. And
it's position 1, so the servers need to be exact replicas of each other.
Right. So it needs to be sort of a lockstep sort of. Right. We're now. So this is also what like that front end thing does, is it tells the servers, okay, you've gotten all of these writes over the last second or 5 seconds. Now update to incorporate all of those. And now requests from now on will be in the next sort of epoch of the database that has these writes applied, so that they're consistent.
Message, I talk to the coordinator.
Right. So I mean, yeah. So how we have it structured is you talk to a coordinator, and your coordinator is defined to have a set of servers behind it, and you need to be encrypting to those same keys that it's going to actually forward your messages to. So right now it would be, and I think. There's the potential to be able to do this with overlapping but not identical sets of servers, but it's not something I've actually thought about how you build, and it's probably non-trivial.
Thanks for the talk.
Yes, if there's no one else, let's give a big hand to Will.
Thanks.